Hello and welcome back to section 3 of the course called Integration of Multiple Microservices. In this section we will see what are the alternative ways to integrate multiple microservices and the pros and cons of each one. We'll also use some of these approaches to extend the services we've already built in the practical examples. In this section we will cover 5 basic parts. We'll start by discussing what are the available methods to integrate our microservices, from high-level concepts such as communication modes to lower-level things such as libraries and frameworks. We will then demonstrate how we can use one of the presented technologies to extend our existing microservice. In the next topic, we will build another service using an asynchronous communication mode as presented before. The next topic will cover monitoring and logging. We will explain why these practices are very useful for a microservices architecture and give some best practices. In the last part, we will see how we can implement monitoring easily using an AWS service called CloudWatch. In this first part, we will talk about the various methods that we can use in order to integrate multiple microservices, the trade-offs, and some guidelines that can help us make the right choice. We'll start by examining the two main communication methods. Two systems can communicate with each other, either synchronously or asynchronously. We'll use the generic term actor here, which can mean a thread, a process, or a server, but you can think of actors as services deployed to different machines. In a synchronous model, an actor makes a request to another actor and then has to wait for the response until it's able to execute something more. On the other hand, in an asynchronous model, an actor is capable of sending that request, and as soon as the second actor has acknowledged receiving the request, it's able to start doing other things. When the second actor has completed processing the request, it will send a notification back. If the first actor is interested in the result of the request, it will be able to process it at that point. There are multiple mechanisms for that, such as callbacks, futures, etc. But we won't go into technical details here. Let's have a look at the basic pros and cons of each approach. The synchronous model is much easier to reason about since the execution is linear and easier to follow. It's also easier to implement since most programming environments use a synchronous model for all the calls by default. However, this model usually leaves less space for concurrency, since we can always do one thing at a time. On the other hand, the asynchronous model is much more efficient since we are able to leverage parallelism and make a lot of things while waiting for responses from other systems. It's also a very suitable model for long-running jobs, where we are not able to maintain a persistent connection for long periods. However, this model introduces a lot of complexity which can lead to anti-patterns such as the callback hell. However, there's been significant progress on that front, and there are a lot of libraries now that provide nice abstractions, such as the completable future API of Java. Note though that asynchronous APIs are almost always harder to troubleshoot and test when compared to synchronous ones. Going a step up, we will now look at a higher level concept, this of a communication workflow. This determines how more than two services can cooperate for a common goal. As you can see, there are two main workflows. The first one is called orchestration. It's based on having a single service which plays the role of the orchestrator and combines the request from multiple sub-services to provide a final result, as we can see in the slide. The second one is called choreography. It's based on having multiple services where each one plays its own role. For instance, when there is an incoming request, Service A would receive it, perform some processing for its own purposes, and then pass it on to Service B. That service performs its own processing as well, and then passes the request on. This goes on and on until all the processes have processed the request. That transition of the request between the various services is usually done with the help of a messaging system, which can hold multiple events at a time and pass them on when the next service has capacity to process them. It's important to note that these approaches can be combined with any of the communication modes we presented previously. For example, the orchestrator could use synchronous calls, but it could also make all the requests in parallel and combine them in the end using asynchronous communication. Here are some of the pros and cons of each approach. The orchestration is simpler to understand and the business logic is testable very easily since it's all encapsulated in a single service. However, it can end up being harder to evolve and extend since the orchestration service usually ends up having too much logic, making it difficult to add new responsibilities every time. This approach can be a good fit for cases where we want to perform aggregations. For instance, imagine an e-commerce website which contains a set of products, along with recommendations for the customers and third-party ads. That could be served by an orchestrator service, which would be responsible for collecting all that data from multiple providers in an efficient way. The choreography approach promotes loose coupling between services when done properly. This is because each service needs to only be aware of the message that's transferred, and does not need to know what are the operations of downstream services. It's also quite resilient to failures. A service can have an outage without causing failures to the whole system. Messages will just get accumulated in a single place for that duration, and the service will catch up when it recovers. However, as you can see, it's harder to troubleshoot and test, since an operation now is split between multiple services. Another drawback is that it takes more time to see the results from the incoming request, which can be confusing sometimes. This approach is very suitable for modeling business workflows that are by nature asynchronous. For example, an order of a physical product has to go through several stages, such as order sent, order approved, order shipped, etc. And customers already expect for this whole process to take a while. As a result, modeling each stage as a separate service and connecting them via a messaging system seems a good approach. Let's also have a look on the two main styles we can use to actually send data between two systems, REST and RPC. The first one stands for Representational State Transfer. The main idea behind it is to model your systems as resources and actions on these resources. Note that REST is technology agnostic and can be implemented on top of any protocol. However, HTTP provides a lot of infrastructure which can be used to implement REST easily, such as HTTP verbs and URLs for resources. One important principle of REST is hypermedia as the engine of application state, abbreviated as HATEOS. What that practically means is that we can refer to a resource from a different system in our response via a regular URL, the way web pages can link to other web pages. In our example here, you can see that the song resource refers to the author of a song via a URL, which could be resolved by another service. Last but not least, the media type that's used in the response should be independent of how data is stored physically to avoid coupling. RPC, which stands for Remote Procedure Call, takes a different approach. In this style, we represent data transfer as actual method calls. This allows us to design cleaner interfaces and help our clients understand better our service, while also providing type safety. In order to avoid writing a lot of boilerplate code, RPC libraries usually come up with code generation tools. As a result, we only have to write a definition of our service interfaces and the models of our data. From these, we can generate code that our clients can directly use to perform calls to our service. One of these frameworks is called gRPC, and we'll see how we can use it later on. As we mentioned previously, HTTP provides a nice foundation to implement REST quickly and easily. When following the HATEOS principle, we can decouple our systems, since services don't need to know about other services anymore and can only refer to URLs. Because of HTTP, there is also a better toolset for development and troubleshooting. However, REST can be inefficient at times because splitting our interfaces based on resources can force us to make many more network calls. Furthermore, some things cannot be modeled as resources, such as the operation of printing a document. Lastly, because of its distributed nature and fine-grained interfaces, it's not very suitable for implementing transactional semantics. For RPC, as we said previously, it encourages services to provide specific contracts and makes interfaces easier to understand. It can also reduce defects, not only because of the strong typing, but also because RPC frameworks usually provide other common functionalities which can be tricky to implement. Because of that and the fact that a lot of code is auto-generated, it can save significant development effort. On the other hand, it introduces one more step in our development process, making it more complex and perhaps slower. Another risk is that developers can get accustomed to the illusion of making local calls, ignoring factors such as network latency, failures, etc. Also, there are a few RPC frameworks that are not interoperable with many languages. One classical example is the RMI framework, which is only available in Java. In this video, we've described and compared the main approaches for integrating different microservices.